Hello. Yeah, good start. Grab a seat. We're good to go.
Okay, hello everybody. My name's Tom Johnson. I'm here to talk about some stuff I've been doing recently in Haskell, developing an entity controller game engine. And just to give some background, this has been sort of like my introduction to Haskell. So we had a lunchtime Haskell study group, and after having gone through Learn Your Haskell for Great Good, we thought, okay, well, let's try and build something of our own, build an application. And a game seemed like a really interesting thing to do because that can get big and complicated. And what we found was that we hit some really interesting scaling problems in terms of structuring it and making it easy to understand. So that's basically what I'm going to be talking about. In terms of my credentials, it's really important to understand where I'm coming from because I basically have no idea what I'm doing here. I'm sure that I'm going to mention some things you're going to look at and say, that's silly, there's much better ways of doing it in Haskell. I'm going to say other things that are obvious, but I'm using completely the wrong names for. Please, bear with me. Let's see if we can talk about the fundamental concept. So, what is a game? This is a really big thing, and I'm going to gloss over a huge number of the details. The first thing I'm going to gloss over is Gloss, which is the game library that we used for the basic game loop. So game updates 60 times a second, draws the screen. So given some data, a way of drawing it, response to input events, and response to the passage of time, that's basically sums up your game. So you could express it that if you've got a game, as long as it's got a render and on input and a time step function, that's all you need. I'm not going to talk about rendering. I'm not going to be talking about how you get the game loop or anything like that. I'm just going to be talking about how we handle the game logic. So let's take a really simple game like Pong. So Pong, is everybody here familiar with Pong? Anybody not? Okay, so you can sum that up quite straightforwardly with a data structure. You've got two bats, you've got a ball, and you've got some scores. And the ball is basically, it's just got a position, it moves, and it's got a shape. And we can start by writing functions like this. So given Pong, which is our game, when there's an event, then you get an IO Pong back out again. So in this case, if the up button's been pressed, you move up. If the down button's been pressed, you move down. Otherwise, it just remains unchanged. And you can write a whole bunch of functions like that to define your inputs, define your outputs with nice little functions like this. And you've composed a very basic game. I would rewrite it like this, which then allows us to sort of like express things in a much more composable thing. You can easily, some of these things don't need to be I/O, so we can use fmap instead of bind. You can comment stuff out and it still works. You can add things in, it diffs nicely. So this is a really nice sort of like structure for building a game that's just a composite of various different handlers. So that's all well and good, and that works pretty quickly. It gets a bit more interesting when you get to something like Pac-Man, because Pac-Man's a much more complicated application. You've got like a title screen. Did you know Pac-Man had cutscenes? And you've got different levels, some of which don't work in this particular instance. So if we were to start thinking about what this looks like, okay, you want to control flow between screens, you'll have high scores at the very top level in persistent state. Then within a screen, I have a title screen or high scores, and then a game which has got the actual game state, which will track things like your lives, your score, which maze you're in, and then the maze is going to have some state in there as well. So the sorts of functions that we were writing before, where we were just sort of like modifying the bat and the object, they get complicated really quickly. This is where we talk about lenses, monad transformers, all the usual Haskell stuff. You're sort of really familiar with all of this stuff. We can just write an update maze function and have that just compose the lenses up to the top level, and we've still got a handler on the top level, which is nice and clean. The trouble is that game events tend to be sort of like far-reaching and affect things across the thing. So if we have a look at a situation where we want to, say, a Pac-Man and Ghost interact. So there could have been one or two things. It could be that the Pac-Man was, powered up. You eat the ghost and your score goes up, and the ghost. Or it could be that you weren't powered up, in which case you lose a life, which means then you update the high scores and you're back to the table. And okay, right now this thing that has effects goes all the way up to the top. So if we sort of like change the way we think about this and instead think about, okay, well maybe these things can fire events. Events is just a writer T of game events. So Whenever one of these things happens, you put a new event at the back of a list. Once you finish doing that, you run through all the game events in another game event function. Well, if you're doing that, you might as well just say, okay, well, time step and input events are game events too. So you've got this sort of like function reactive loop of events that are happening. Then you get the question of how to represent the game events, because the obvious thing is to start off with an algebraic data type, because we all love those. But it turns out that actually, as the application scales, this scales really poorly, because algebraic data types kind of suck. And the problem with this is that you've got all these various different things. Every time you want to add a new event anywhere in the system, you need to go back and modify this list here. And often you have things like libraries, like, okay, well, you've got the basic game loop stuff, which handles the time step in the input. You might have a timer, you might have collision detection. You want to be able to compose these things with an event which also includes things that are very specific to your individual game. You also have another problem, and this is kind of a nitpick, is that every time you write a function that deals with a game event, you've got to write this bit down here, which is a bit of a pain in the neck. So this is where I started exploring dynamic types, because there's nothing Haskell is like quite more than dynamic typing. If we use dynamic to represent our events, you rewrite it to this sort of thing, then we don't have to be specific about what an event is. We can have different ideas of what an event is at different parts of the library, and they still compose, because the only things that deal with the events that are being fired are the ones that are expected to do like that. We still have this bit down here, which I don't really like. But if you write 2 or 3 of these functions, you notice that actually this whole block here is repeated every single time. And you can abstract that out into a function, which I called focus. And this, the thing that's useful about this is we know what to do with an event if we don't understand it, which is we carry on doing what we were doing before. We just let the object pass through. This allows us to then write functions like this, where all we're doing is we're saying, okay, well, this is the event that triggers us, and then you get a very, very straightforward function which just deals with that small lensed-in aspect of what we're dealing with. We don't need to do the, well, what if it's not the sort of thing I'm expecting to handle? That's handled via the focus. And if we just put another little combinator in there, that makes life an awful lot easier. What I've done here actually is I've taken this function of event to an object to events of an object, and called that a Redux, which was inspired by Redux React sort of stuff. And that allows us to then say, okay, well, as far as the user is concerned, they don't even need to care what the implementation is. And actually, in later versions of this, Redux isn't even a function. And then you can just, the whole thing is abstracted away from the user. You can write very, very compact functions that you then just compose in exactly the same way, sequenced, and you don't even need to write, so it's like start, then this function, then this function, then this function. It just works. So let's talk about something a bit more complicated. So the thing about Mario is there's an awful lot of diverse different sorts of things that you guess in here. One question is how do you store them? You could do something like this, which works kind of well with Pac-Man, but when you start to get hundreds of different game objects, it gets much more complicated. You could do something where it's just one game object, but you've got one big ADT, same sort of problems. And the game logic is particularly awkward here because, like, say, take here, the top row, those float, bottom row, they fall. Top row, they hurt Mario. Bottom row, they don't. Top row, they move. Bottom row, they don't. And scaling this sort of game logic doesn't work really particularly nicely with type classes, at least not in any way I've been able to find out how to use them, because you need to sort of like discriminate the types at compile time. Object-oriented doesn't really help either, because the way that these behaviors compose is not hierarchical. It's not like this thing has this and then all these other things follow. It's taking stuff from all over the place, which is where entities come in. I'll call it the bag of stuff pattern. This is sort of like a standard way of doing it within games engines. And you've got these 2 basic functions on an entity. So this is a little bit like dynamic. So if you've got a Mario, then you can try and get the triforce off it. There's nothing there. You can get the position from it, and that gives you the position. So far, so much like dynamic. But you can also have other things in it as well. And you can actually end up with a whole situation where different things have got different components in different ways. So like all of these things have a position. They've all got a sprite, but none of them have an acceleration. Some of them are deadly, some of them aren't. And if we had a function like this, which takes a time step and then a combination of position and velocity, we could say, okay, well, we want that function to apply to these objects, but not the rest. And then update the position. Or something which takes a velocity and it doesn't fly. Okay, well, those things have velocity. Bullet bill also has velocity, but flies, so it doesn't count. And then you set the acceleration. So how do we actually do that? And here's a really basic sort of way of doing it. This is the easiest to explain, but it's not a very efficient way of doing it, which is have the entity being a list of dynamic. And so get component, if it's an empty list, it's not there. And otherwise, you try and get the first thing. If it's of that type, return it. Otherwise, recurse down. And that gives you a way of storing sort of like this untyped heterogeneous container of things in a way that's sort of type safe. If we make it constrained dynamic so that we can put a type class on it, then got those out of order. Then we can also do things like override the get method so that you can get a tuple which pulls out the two different things, and if they're both there, you get the thing, and if either are missing, then you don't. Or not, which says, well, we'll get a not back if it's not there, but not a not back if it is. Basic function like this, which says, okay, well, let's given an entity, let's try and get those things out of it. If we can get them, apply the function, then set them back on the entity. Otherwise, just return the entity, apply it to all the entities, and then you can have a situation where you can write these functions which just then take your entire collection of things, apply the transformations to the ones which match the type, and the other ones just ignore it completely. And then a little combinator. So, for example, let's do. This is a really basic game because I spent more time working on the engine than working on the on graphics or levels or fun, which perhaps I should go back to. And if we have a look at the code, like the point I want to make here is that, take this for example, this is written like in terms of incredibly simple functions that you can understand by themselves, and they just compose into these reduxes. And these reduxes just compose into a larger application. And it's just, and the point I'm trying to get over here is that this provides a really straightforward and easy to pick up developer experience with it. There are ways of making it much more efficient, which I can talk about later if you're interested. But it provides a really, really clean way of scaling logic in a way that's, oh, I'm out of time. So that's what I had to say. Okay, you're up next.